Okay, in that last episode you got to see me relive the emotional trauma of elementary school. That was fun, and it made me realize something. Despite all the stuff I've learned since elementary school, I still don't have a good way of doing basic multiplication. That fact really started eating at me, so I spent a few days looking up alternative forms of multiplication. What I found is that I'm not the only person with this grievance. It seems like nobody has invented a good way of multiplying small numbers yet. That fact really bothers me. It's like, how did we, as a species, somehow manage to cure polio, split the atom, and land on the moon without first working out a good way of multiplying 6 by 7? I have no explanation. What I do have for my investigations are some handy new tricks for multiplying big numbers. It turns out that while nobody knows how to multiply 7 by 8, it's actually pretty easy to multiply 928,556,321 by 11. Go figure. Now, I found 4 methods for alternative multiplication, but I can't really do any of them justice without spending at least 5 minutes on each. That means I'm going to be running my mouth for about 20 minutes. Since my audience is the internet, and since the internet only has the attention span of one loop of Beyond Cat, I've decided to split this into 2 episodes to keep things manageable. That means you people get an extra episode. You're welcome. Alright, first new strategy. In the 1950s, a Hindu cleric named Bharati Krishna Tirthaji wrote a book on mathematical shortcuts with the controversial title Vedic Mathematics. Controversial because Tirthaji claimed that all the rules in his book were rules he discovered in the ancient Hindu religious texts, or Vedas. That claim of ancient Indian origin has fallen under certain criticism in the years since because Tirthaji kinda didn't provide any proof that his rules were actually ancient and was also possibly politically motivated to say that they were. But I left my asbestos raincoat at home today, so we're just going to sidestep that flame war and cut straight to the mathematics. Tirthaji's rules for multiplication involve using what are called the tens complements of numbers. In other words, the amount that a number is below 10. So, for example, the tens complement of the number 7 is 3, tens complement of 8 is 2, tens complement of 9 is 1, and so on. Now, just to muddy things up a little, we're actually going to use the negative of the tens complement in our calculations. There's no good word for the negative tens complement, so you can call it whatever you want, like the partner number or something. So since 8 is 2 less than 10, we say its partner is negative 2. Since 13 is 3 more than 10, we say its partner is plus 3. Good so far? Okay, so Tirthaji says that if you want to multiply 8 by 7, you start by writing 8 and 7 on top of each other. Then next to those, write down their partners, minus 2 and minus 3. You multiply the 2 partners to get your ones place, 6, and you add the numbers along either diagonal to get the tens place. So you could do 8 minus 3 to get 5, or you could do 7 minus 2 and you'd also get 5. So your answer is 56. Another example, 7 by 7. We write 7 and 7, minus 3 and minus 3. Product of minus 3 with itself is 9, sum of 7 and minus 3 is 4, so the answer is 49. It works for multiplying things where one number is bigger than 10 and the other is less than 10 too, although sometimes those are tricky because there's carrying involved. If you had to do 16 by 8, you would write 16, 8 plus 6 minus 2. So the ones place is minus 12 and the tens place is 14. What that means is that our answer is 12 less than 140, so that's 128. The neat thing about this strategy is that you can use it to solve really big products by extending the idea of tens complements to hundreds complements or thousands complements for numbers close to 100 or 1,000. For example, if you had to do 121 times 104, you'd write 121, 104, plus 21, plus 4. So the last 2 digits are 84, and the first few digits are 125. That makes our answer 12584. Now sometimes it's a little tricky having to deal with the subtraction. For example, if we had to do 94 by 103, we'd write 94 103, minus 6 plus 3, get minus 18 at the end, and 97 in the other digits. So the answer is 18 less than 9700. How do you do that subtraction? Well, 9700 minus 18 is just 9600 plus 100 minus 18, right? So we know our first 2 digits are 9, 6. Now we just have to figure out what 100 minus 18 is. Like I said in the addition and subtraction episode, subtraction is just reverse addition. So the question, what is 100 minus 18, is the same as asking, how much do you have to add to 18 to make it equal 100? Problems like this are nice because all you have to do is figure out what to add to 18 to make the last digit a 10 and all the other digits a 9. You might have learned something similar in school called change from a dollar. Like if something costs 18 cents and you pay with $1, you figure out what the change is by adding to 18 until the tens place is a 9 and the ones place is a 10. It's the same idea here. So that's 82, or 82. That makes our answer 9682. Just as an aside here, we can extend that idea of subtraction to bigger powers of 10 too. If you had to do 1000 minus 758, you just got to make all the other digits 9 and the last digit a 10. So you put a 2 in the hundreds place, since 2 plus 7 is 9. You put a 4 in the tens place, since 4 plus 5 is 9. And you put a 2 in the ones place, since 8 plus 2 is 10. To do 100,000 minus 56743, you'd write your answer as 43257. Okay, so that's Tirthaji's multiplication in a nutshell. Write the numbers with their partners, multiply the partners, and then add either partner to its diagonal number. And wherever subtraction's involved, you use the 9 or 10's complements, change from $1. For small products, this method might be more effort than it's worth since you have to picture 4 numbers in your head all at once. For big products, it's a lot more useful, although sometimes when you're doing the subtraction you can get lost. At the very least, it makes doing calculations on paper a lot faster. Alright, now around the same time Tirthaji wrote his book, half a world away a new type of mental calculation was being developed. Yakov Trachtenberg was a Russian engineer who developed his own method of doing multiplication in his head as a way of distracting himself from the fact that he was being held prisoner in a Nazi concentration camp. Wow, this episode just got dark. But Trachtenberg escaped captivity, made his way to freedom, and published his technique for doing mental math. Ballin'. Alright, let's see how it works. Let's say you have a big number times a small number. You start by putting zeros on either side of the big number. There's a leading 0 to the left and a 0 after the decimal point to the right, so we haven't actually changed the value of the big number at all. We just changed how we wrote it. Now, we'll generate our answer one digit at a time by combining pairs of neighboring digits. The way in which we combine these digits depends on what the small number is that we're multiplying by. In this case, our small number is 10, so the rule for combining neighboring digits is really easy. You just write down the right digit plus 0 times the left digit. In other words, you just write down the right digit. So working from right to left, that's 0, 4, 3, 2, 1. So our answer is 12340. That probably seems like a lot of effort for just multiplying something by 10, so let's do another example. 1234 times 11. Start by padding the big number with 0, so it's 01234.0. Now look at the rule for multiplying by 11. To do that, we combine pairs of digits by doing the right digit plus the left digit. So that's 0 plus 4 is 4, 4 plus 3 is 7, 3 plus 2 is 5, 2 plus 1 is 3, and 1 plus 0 is 1. So our answer is 13574. The pattern continues as the number we're multiplying by gets bigger. The rule for multiplying by 10 was right plus 0 times left. The rule for multiplying by 11 was right plus 1 times left. So the rule for multiplying by 12 is right plus 2 times left. So to do 1234 times 12, start with your padded zeros, then do 0 plus 2 times 4, that's 8, 4 plus 2 times 3, that's 4 and 6 is 10, so we drop the 0 and carry the 1, 3 plus 2 times 2 is 7, with our carry makes it 8, 2 plus 2 times 1 is 4, and 1 plus 2 times 0 is 1. So our answer is 14808. Now, the carrying can get a little annoying, but Trachtenberg never multiplies by anything except 0, 1, 2, or 1/2. So if you have to do carrying, it will only ever be a 1 or a 2, so it's not that bad. To do products where the number we're multiplying by is less than 10, we have to do the right digit minus some multiple of the left digit. But how do we do a negative of the left digit? Turns out we already seen how to do that. You just use that number's 9 or 10's complement like we saw in Tirthaji's method. So to do 1234 times 9, the rule is to do the right digit plus the left digit's complement. For the left digit of the first pair of numbers, we need to use the 10's complement, and for all other pairs, we use the 9's complement. So we find our answer as 0 plus 6 is 6, 4 plus 6 is 10, drop 0, carry 1, 3 plus 7 is 10, with our carry is 11, drop 1, carry 1, 2 plus 8 is 10, with our carry is 11, drop 1, carry 1. And now our last step is a little different. We've been doing subtraction this whole time by forming 9's complements, but the only way we were able to do that was by borrowing from the next biggest digit. But here we're at the biggest digit. This is the end of the line. We've run out of places to borrow things from. Our biggest digit has to pay the bill then and get reduced by 1. But we've also carried a 1 here, so those two facts end up canceling each other out, and our biggest digit is just a 1. So then our whole answer is 11106. Doing multiples of 8 follows the same pattern. We just do right plus 2 times left complement. So you do 1234 times 8 as 0 plus twice 6 is 12, and so on. Now, Trachtenberg doesn't like having to multiply by anything bigger than 2, so while you could try to do products of 7 by doing right plus 3 times left complement, that seems like too much work. Instead, he's got a different solution. Let's start by talking about products of 5. The rule Trachtenberg came up with for those is you just use half the right digit, then you add 5 if the left digit is odd. So 1234 times 5 gets you half 0 is 0, 4 is even, so 0. Half 4 is 2, 3 is odd, so 7. Half 3 is 1, we're rounding down here. 2 is even, so 1. Half 2 is 1, 1 is odd, so 6. So our answer is 6170. To do products of 6, you do half right plus 1 times left, with the possible addition of 5. And to do products of 7, you do half right plus 2 times left, with a possible plus 5. So to do 1, 2, 3, 4 times 7, you do half 0 is 0, plus 2 times 4 is 8. 4 is even, so 8. Half 4 is 2, plus 2 times 3 is 6. 6 and 2 makes 8, plus 5 is 13. Drop the 3, carry the 1, and so on. You might find it easier to do the steps in a different order. I find it easier to start by multiplying 2 times the left digit, then add half the right digit, then add the 5 if I need to. So I'll do this as 8 and half 0 is 8, 6 plus half 4 is 8, plus 5 is 13, drop 3, carry 1, 4 and half 3 is 5, with carry is 6, 2 and half 2 is 3, plus 5 is 8, so 8, 6, 3, 8. This probably sounds pretty tedious, but it gets easier with practice, and also this is about as complicated as it gets. Well, unless you're trying to multiply by something slightly smaller than 5. Then it gets worse. The rule for multiplying by 4 is half right plus 1 times left complement, and the rule for multiplying by 3 is half right plus 2 times left complement. So you can see how the rules work. Every time the number we're multiplying by goes up by 1, you tack on an extra left digit. Every time it goes down by 1, you tack on another left digit complement. By mixing and matching the rules, you can generate new rules for any small number you want. So that's Trachtenberg's method. The advantage is that it reduces the problem of multiplying by any number into a problem of multiplying only by 0, 1, 2, or 1/2. And you only have to operate on a single pair of digits at a time. The downsides are that you can't really do this using only your imagination. You have to write each digit down as you calculate it, or else you forget what your answer is. Also, this method requires you to get good with 10s and 9s complements before you can do it quickly. So like with Tirthaji's method, this strategy isn't a silver bullet to multiplication. It has its strengths, and it has its weaknesses. Alright, next episode I get my ass kicked by 7-year-olds, and you get to learn how to do magic. Stay tuned.